Hey everybody, it's Mr. Cargan. Today we're going to be looking at more with our logarithm functions, our logarithmic functions, but instead of just what we did before, which was evaluate our expressions, now we get to sketch and analyze graphs of our logarithmic functions. Okay, so our basic ideas of logarithmic growth and decay look like this. So if we have f of x is equal to log base b of x, as long as b is greater than 1. And it looks like this. We have an x-intercept at 1, 0. We actually will not have a y-intercept, okay? And our end behaviors, you look at that as x approaches, so this end behavior is x approaches 0, f of x is going off to a negative infinity. So this is a little bit different. We are approaching 0 from this positive number here for our limit. So it's a little bit different than our other limits because we would go off to a negative infinity. While the end of this graph is not approaching negative infinity, it's approaching 0, but it can't actually equal 0. Big reason is because we cannot plug in x equals 0 here. Okay, we cannot take x equal to 0. So it's kind of like a vertical asymptote, basically, which in this case, yeah, it's y-axis for that. Okay. It is continuous going from 0 to infinity. Okay. If this is a growth one, so it's going left to right, it's increasing. A decay function goes left to right, it's decreasing. Okay, but it's very similar with all those. So with the decay versus growth, we see that my base numbers are very specific. If the base number is greater than 1, we get a growth. If it's in between 0 and 1, any kind of fraction or decimal, then it's going to be a decay one. Okay. So when I look at these, one thing that help us realize the one thing that's going to help us with graphing this is recognizing what is a logarithmic function as a graph. So it says here we want to sketch and analyze the graph of f of x equals log base 2 of x. Look at domain, range, intercepts, asymptotes, and behavior, and where the function is increasing or decreasing. The thing that's going to help me graph this is actually figuring out the inverse of this logarithmic function, which is the exponential function. Okay, so the inverse of this function, if this is log base 2 of x, I guess the inverse function is actually going to be 2 to the x. Okay, oops, let me write. There you go. The inverse function is actually 2 to the x power. So let's go to Desmos real quick to help us with that. So here's 2 to the x. Here's log base 2 to the x. So remember what it means to be inverse. It is reflecting over this line. So for every point that's on the graph, so 0, 1, it goes over here to 1, 0. Okay, if I go 2 to, if I plug in 1, that's 1 to this first power, so that is going to equal to 2. Okay, so it's going to be right about, there we go, 1, 2. So the inverse of that, or the reflection of that is going to go to 2, 1. That's, come here. There we go. Right there. Okay. So we get these reflections over that line. So that's going to help us kind of understand how to graph this a little bit better if we know those values. So for example, let me do like I'll just do an xy, but this is going to be for 2 to the x. Okay. So if I do, for example, negative, whoops. Let's go with like -2. 2 to the -2 power is 1/4. If I go to -1, that's going to be 1/2. 2 to the 0 power is 1. 2 to the first power is 2, and then 2 to the second power is 4. So that's 2 to the x. But when I do log base 2 of x, we are going to get all these are going to reflect over x equals y, meaning 1/4 for x is going to come out to -2 for y. 1/2 for x is going to be -1 for y. 1 will go to 0, 2 will go to 1, 4 will go to 2. So this is a way I can find my points a little bit more easily and go ahead and graph those. So I've got 1, 0. I've got 1/4 -2. So we'll say about right here. Here's my 1/2 -1, 2, 1, and 4, 2. Okay. So there's my exponential growth function. I'm going to go ahead and move this over a little bit. I need a bit more space here. So now I can go through and analyze all my pieces. So we want domain. So domain, the only restriction is I can't plug in 0 for x, but I can go on forever to the right. So it's 0 to infinity. My range is not restricted at all. This is going to go down forever and it's going to go up forever. So it's going to be negative infinity to infinity. For my intercepts, I have just one intercept because, again, I cannot plug 0 in for x. So I've got the point 1, 0. Asymptotes. Okay, I have one asymptote, and that is the y-axis, or x equals 0. Okay, and behavior. So remember, there's going to be, this one's a little bit different on the cases here. So I'm going to analyze the limit as x approaches infinity. I'll do that one because that one's a little bit easier. As x goes off to infinity, f of x will continue up forever. So f of x will equal to infinity. But the left-hand limit is not going to go to negative infinity. It's going to approach 0. I didn't mention this earlier, but x is going to approach 0 from the positive direction. Okay. If this graph were to flip over and does something like this, it would be approaching 0 from the negative direction. So that's what this notation means. X is approaching 0 from the positive direction. That is basically saying right to left. So that means f of x is equal to negative infinity for that one. Okay. So that's end behavior, and it's increasing. And so that means it is increasing here forever from 0 to infinity. Okay. And that's it. So we're going to do the same thing here. We're going to graph this one. Again, use the idea of what is the inverse function here. G of negative 1 of x. If this is base 1/3, it's going to be the same as 1, or the inverse is going to be 1/3 to the x power, which is an exponential decay function. Okay. So let's go to Desmos real quick just to see that, but we can use that as guidance as well. So here is 1/3 to the x power. And then here is 1/3 base, log base 1/3 to the x power. So in this case, you can see how they cross at the same point right here. Okay. So it's crossing at that point. So it's going to flip over that line right there. So we can look at this and help us analyze that with our graph of this one. Okay. So if I graph the idea, so again, I'm going to go ahead and figure out some points for x and g of x here. So I'm going to pick some easy ones for that. So if I do like -1, that goes up to 3, or sorry, let's go -2, goes up to, that's going to take me off. We'll start at -1. -1 is go to 3. 0 is going to go to 1. 1 will go to 1/3. 2 will go to 1/9, and so on. Okay. That's my g of x. Sorry. That was my inverse function I was just doing. Inverse of that. So this is 1/3 to the x power. Okay. So instead of using 1/3, I'm going to use that to help me with my other graph. So since my x and g of x here, that means 3 will go to -1. 1 is 0. 1/3 will go to 1. And then 1/9 will go to 2. Okay. So that means if I plot those points, I've got 3, -1, 1, 0. I've got 1/3 is 1, 1/9 is 2. So it'd be something like this. So that's enough to get my sketch. Okay. So same thing as before, we're going to find all of our key characteristics. Domain, same thing as before. Can't be 0, but we'll go on to infinity to positive infinity. Range, there is no limit, so it's negative infinity to infinity. For my intercepts, I have only one intercept, and that is at 1, 0. Asymptotes. Once again, that is just going to be the y-axis, so that will be x equals 0. End behavior. Okay, so again, I got the interesting one here because the limit as x approaches infinity, f of x will equal to a negative infinity. Okay, that's my decay here. It's going to go off to a negative infinity. But the limit as x approaches 0 from a positive direction, f of x will equal to a positive infinity. So I'm approaching 0 from the right, and it's going to go up forever. Okay. And then this function is decreasing for the entire domain. So 0 to infinity. So that's our two basic growth and decay functions, along with all of our characteristics that we've been analyzing with all of our functions so far. Let's go ahead and look at some transformations of these graphs. So graph a transformation of a logarithmic function. So if we have, oh, sorry, good. Looks like this. Oh, there we go. So a little frozen. If we have a graph f of x equals log of x, describe the transformation if we go negative log of x minus 2. So this function is going to be kind of like with our other ideas with a, h, and k. We can have f of x is equal to a times the log of x minus h plus k. So we can do the same exact things that we've done before with those. Since a is a negative number, a is less than 0, that's going to reflect over the x-axis, which we can see here. If this is my log of x function, it flips it over and goes this way now. Kind of like it's just basically a decay function. Okay. Then, so that's our, let's see here. If we look at inside here, we got x minus h, that would cause a horizontal translation. We don't have that here, but we do have minus 2 at the end. So it reflects over the x-axis, and then because we have a k equal to a negative 2, it translates down 2. Okay, so that's our description there. And again, you can see how that worked. Here's my original parent function, log of x. It flipped over and then translated down 2. So really, it flipped over and did this, and then everything moved down 2 from there. All right, so let's look at this one. Same idea. So if f of x, or sorry, the log of x is our normal function, we want to look at 5 times the log of x minus 3. So a is equal to 5, which means a is greater than 1. So just like we saw in the previously in other functions, if a is greater than 1, this causes a vertical stretch by a factor of 5. We have x minus 3 inside those parentheses here. So the whole graph is going to go 3 to the right. It's going to go opposite the direction that we would expect on that one. So h is equal to, in this case, h equals 3. So it has a horizontal translation 3 to the right. Okay, so again, here's what we're seeing here. Here's my normal logarithmic function. If we take it 3 to the right, then this value here was 1, 0. It goes 1, 2, 3. It's now crossing at 4, 0. But then we take it and we stretch it up. And that's why it gets this nice long curve now versus this like more flat curve. Okay, so that's where we're getting those from. So just like our other transformations in the past. Let's also take a look at a word problem for this. And this will be our last example for this one. Okay, so the Richter scale measures the intensity R of an earthquake. The Richter scale uses the formula R equals log of A over T plus B, where A is the amplitude of the vertical ground motion, T is the period in seconds, and B is a factor that accounts for the weakening of seismic waves. A city is not concerned about earthquakes with an intensity of less than 3.5. All right, so an earthquake occurs with an amplitude of 125. So that's going to be A equals 125. A period of 0.33 seconds. So that's the amount of time it takes for it to do a full wave there. So that's going to be my T here. T equals 0.33. And B is just 1.2. So let's find the intensity of this earthquake here. So that means R will equal to the log of 125 divided by 0.33 plus 1.2. This just turns into a calculator problem at this point. We have all the information we need. We're just going to plug it in and make sure you do the log correctly. So it might help if I do this first. Do log of, if we take 125 divided by 0.33, we get 378. I'll be 78 repeated. So now I make sure I do the log of that value. So you're using log base 10. And then I'm going to add 1.2 to that. And I get a Richter scale of 3.78. So a city is not concerned about the earthquake with an intensity of less than 3.5. Should this earthquake be a concern? Yes. The intensity is 3 point, well, okay, I guess I could go 3.8, which is greater than 3.5. Okay, so that is what we're looking at for these types of problems. So these word problems are usually straightforward. You're just going to work with your log buttons and make sure you simplify it correctly. Okay, but that's basically it for today. We're just analyzing our logarithmic functions. How do we transform them? And then using them to model in our real life cases like this. All right, that's it for today. Take care, everyone.